Let's take a look at relativistic mass. At rest, a particle has rest mass m0. But when it is moving, its mass m could be different from m0. To investigate this, consider a glancing collision between identical particles of rest mass m0. Here is the scenario before the collision viewed in frame S. Let particle 1 be a target at rest in S, and let particle 2 be an incident particle of mass m, as measured in S, moving to the right at speed u in the x direction. We assume that m may be different from m0, and this depends only on the speed of the particle. Because the collision is glancing, the incident particle just touches the target particle and nudges it downwards. The incident particle is nudged upwards, but its velocity in the x direction hardly changes. There is an exchange of momentum, so due to momentum conservation in the y direction, 1 gains a little momentum in the negative y direction, and 2 gains the same magnitude of momentum in the positive y direction. There is a negligible exchange of momentum in the x direction, so the x momentum of 1 stays close to 0, and the x momentum of 2 stays close to its initial value, so its speed in the x direction also stays close to its initial value. Here now is the scenario after the collision, still viewed in S. So after the collision, 1 has speed v1 in the negative y direction, and 2 has speed v2 in the positive y direction. Furthermore, because the collision is glancing, the speeds in the y direction after the collision are small compared with u, so the resultant velocity of 2 is very close to its initial velocity. Thus, its final speed is approximately equal to its initial speed u, and therefore its mass m does not change in the collision. In addition, because v1 is small compared with c, the mass of particle 1 does not change from its rest mass m0. Now we view the collision in the co-moving frame S', which moves with particle 2 at speed u in the x direction. In x', before the collision, particle 2 is now the target, at rest with mass m0, and 1 is the incident particle moving to the left with speed u and mass m' as measured in S'. After the collision, in the view of S', it is now 2 that is nudged upwards with speed v2' in the positive y direction, and 1 that is nudged downwards with speed v1' in the negative y direction, but keeps its speed in the x direction, and total speed, both very close to its initial speed u, just as we saw for particle 2 viewed in frame S. The two views of the collision, in frames S and S', are symmetrical and follow the same physics. If the view in S' is rotated through 180 degrees, it shows exactly the same scenario as the view in S. The transformation can also be done by reversing the view horizontally and then vertically. Consequently, we can state that v2' is equal to v1. Also, momentum conservation in the y direction gives mv2 equals m0 v1. Now apply the inverse velocity transformation to the velocity y components. We equate the velocity y components of particle 2 to the associated speeds, so v2y equals v2 and v2y' is equal to v2'. And note that particle 2 is at rest in S', so v2x' is equal to 0. Recall that v2' equals v1, and that mv2 equals m0 v1. The inverse velocity transformation for the velocity y components is v2y equals v2y' divided by gamma into 1 plus u v2x' over c squared. Substitute the speeds for the scalar components. v2 equals v2' divided by gamma into 1 plus u v2x' over c squared, as well as v2x' equals 0, so we have v2 equals v2' over gamma. Then substitute v1 for v2' to yield v2 equals v1 upon gamma. Multiply both sides by m, and equate mv2 with m0 v1 to get mv1 upon gamma equals m0 v1. Then divide both sides by v1 and multiply through by gamma to obtain the final result, m equals gamma m naught, which is the formula for the relativistic mass. Note that gamma equals gamma as a function of u is calculated using the speed of the particle. In this analysis, we chose frame S' to have the same speed as the particle, so the particle was at rest in S', but in general the particle could be moving in S', in which case the Lorentz factor relating frames S and S' would not be the same as the gamma in the formula for relativistic mass. We must therefore distinguish between the Lorentz factor gamma as a function of u that relates frames S and S' and the Lorentz factor gamma as a function of v for a particle moving with speed v in frame S. A convenient notation is to use the subscript u or v in front of gamma instead of writing it as a function of u or v. In this case, the relativistic mass of the particle is written as m equals gamma subscript v multiplied by m naught. Note that, as in the analysis of the glancing collision, if the particle is at rest in S', then the particle speed v equals the S' speed u, so gamma subscript v equals gamma subscript u. In S', the particle has a different speed v', so its Lorentz factor gamma as a function of v' is different from gamma as a function of v in frame S, and therefore its mass m' is also different. We see that mass measured in an inertial frame increases with motion relative to that frame. A particle at rest has rest mass m naught, and as its speed increases, the Lorentz factor for that particle's speed increases, and the mass increases. As its speed approaches the speed of light, its mass tends to infinity. A question you might ask is, where does the extra mass come from? We will find the answer to that when we look at relativistic energy.